Have you ever been there, waiting for an LLM, maybe getting a bit antsy, waiting for it to finish spitting out text?
Oh, absolutely, especially if you've given it a really long prompt or you're like deep into a back and forth.
Yeah, it can feel like things are grinding super slowly behind the curtain. And well, there are technical reasons for that, but one of the really big ones, especially when it's actually generating the text token by token, is this thing called the decoding bottleneck.
That's exactly it. So when the model's generating, it's sequential, right? One token, then the next, then the next. And that step-by-step process, well, it's not ideal for GPUs that love doing things in parallel.
Right.
But the main factor, the thing that really makes it sluggish, is managing the model's memory of the conversation, specifically these key and value states for all the tokens that came before. That's the KV cache.
Ah, the KV cache. And that just keeps growing and growing with every token, right? Whether it's input or output.
Precisely. And the crux of the problem during decoding is that the time it takes to just fetch that massive KV cache from the GPU's main memory, the HBM high bandwidth memory, that fetch time starts to completely dwarf the actual computation time.
So it's not the math that's slow, it's waiting for the data.
Exactly. You're waiting for the data needed for the math. It's the textbook definition of a memory-bound problem.
And I've heard this has gotten worse over time because the GPUs got faster at calculating way quicker when they got faster at accessing memory.
That's the trend, yeah. The compute power, the FOPIs, has rocketed up much faster than memory bandwidth, so this gap widens.
Which makes problems like decoding, where you don't do that much math for each piece of data you load, it makes them hit that memory wall even harder.
Right, we talk about arithmetic intensity operations per byte loaded. Decoding has low arithmetic intensity. You spend most of your time just waiting for memory. It's fundamental.
So, okay, our mission for this deep dive is to really get into a recent academic paper that tackles this decoding bottleneck head on. They're proposing some pretty innovative ways to redesign the attention mechanism itself, specifically for inference, making it more hardware friendly.
Yeah, they introduced two new methods, group tied attention, or GTA, and grouped latent attention, GLA.
Sounds interesting. So we'll dig into the technical reasons why current methods struggle, how these new designs work. Seems like there are some clever insights there, and also the system level stuff needed to make them actually perform fast.
Exactly. And ultimately, see how this aims to give us faster, more scalable LLMs without, hurting the quality of the answers you get from apps you might use every day.
Okay, so let's unpack that difference you mentioned earlier. Decoding versus the initial processing, the prefill. Why is that distinction so critical for performance?
It really comes down to parallelism. During prefill, you have the whole input prompt right there, all the tokens. So you can process them pretty much all at once, calculating their states, doing the attention calculations in big parallel batches.
Makes sense. Lots of work to do at once.
But decoding, it's inherently step-by-step, sequential. To generate token n, you need the output from tokens 1 to n1. Then for token n plus 1, you need 1 to n. You can't really jump ahead.
Ah, okay, so that sequential nature limits how much you can parallel that at each step.
Severely limits it. And that's why the KV cache becomes the star of the show, or maybe the villain at each step.
Right, because you need all that past context for the next word.
Exactly. For every single new token, the attention mechanism has to look at the current query vector, compare it against the key vectors of all the previous tokens,
Okay.
then use those attention scores to combine the value factors of all the previous tokens, and those stored keys and values are the KV cache.
And it grows linearly with sequence length and batch size, too, if you're doing multiple requests.
Yep. So long conversations, long documents, big batches of users, that cache can get enormous really fast.
And that's where the memory wall hits hard during decoding.
That's it. Each step, the actual math is fairly small, mostly a matrix vector multiply. But fetching the necessary chunk of that huge KV cache from HBM, that's the slow part. The data movement takes longer than the calculation itself.
So those fancy, powerful tensor cores on, say, an H100 GPU are just idling, waiting for data.
In a memory-bound workload like decoding, yeah, that's largely what happens. They finish their work quickly and then wait. And because that compute memory gap keeps growing, the problem just gets proportionally worse with new hardware, unless we change the approach.
Which leads back to that low arithmetic intensity. Not enough crunching per byte fetched.
Precisely.
And you mentioned this isn't just some abstract hardware issue. It affects real applications.
Definitely. Think about chatbots. You want a fast reply, right? That's latency. LLM agents making decisions need quick turnarounds.
Yeah, waiting kills the flow.
And if you're running a service with lots of users, high throughput matters. How many tokens per second can you generate overall? That's constrained by decoding speed. And obviously, dealing with super long documents or chat histories, directly hits this KV cache size limit.
So clearly a known problem. What did people try before? What were some of the earlier stabs at making attention faster for inference, and I guess what were their downsides?
Well, one of the first big ideas was multi-query attention, MQA. Standard attention, multi-head attention, or MHA, has, separate key and value heads for every query head.
Right.
MQA basically said, hold on, let's just use one single key head and one single value head and share them across all the query heads.
Okay, intuitively, sharing 1K and V sounds like it would shrink the cache a lot.
It does, dramatically. You store just 1K and 1 V vector per token, total, big reduction in the KV cache size. And because you reuse that single KV state for all queries, you also increase the arithmetic intensity, more computation per byte loaded.
But there's always a but, right? What's the catch with MQA? I know it's not always perfect quality-wise.
That's the main trade-off, yeah. Forcing everything through one shared KV can sometimes limit the model's ability to capture diverse patterns, potentially hurting quality compared to standard MHA.
Okay.
And there was another issue, especially for big models run on multiple GPUs using tensor parallelism. That single KV head, it needed to be copied, replicated onto every single GPU in the parallel group.
Ah, so all the query heads on each GPU could access it, but that duplication eats into the memory savings system-wide, right?
Exactly. It limited the overall memory benefit across the whole cluster and caused some inefficiencies in how the work was parallelized.
Which I guess led to GQA, grouped query attention, sort of a middle ground.
Precisely. GQA was developed as a compromise. Instead of just one shared KV head like MQA or one per query head like MHA, GQA groups the query heads together. Each group then shares its own distinct KV head.
Okay, so multiple groups, multiple KV heads, but fewer than MHA.
Right, so you still get KV cache reduction compared to MHA, but having multiple distinct KV heads often helps preserve model quality better than the single head in MQA, and critically, it parallelizes better.
How so?
Because you have these distinct KV groups, you can actually shard them or split them across the different GPUs in a tensor parallel setup. GPU 1 handles the KV cache for group 1, GPU 2 for group 2, and so on.
Okay, that sounds more distributed. But GQA still wasn't the final answer. It had limits too.
Yeah, I mean, it's a good improvement, widely used now, but the memory saving is proportional to the number of groups you use. If you only have, say, 2 or 4 GPUs for tensor parallelism, the amount of KV cache each GPU still has to hold for long sequences or big batches can be pretty large.
Right, you need a lot of GPUs, a high degree of tensor parallelism before the per GPU cache really shrinks significantly with GQA.
Exactly.
And then there was another approach mentioned, MLA, multi-head latent attention. That one sounds different, like it compresses things.
Yeah, MLA, which you see in models like DeepSeek V2, takes a fundamentally different tack. Instead of storing the full key and value vectors for each token, it tries to compress the important information from each token into a single, much smaller, low-rank latent vector.
Okay, so you cache just this small latent vector per token.
Right. And then during decoding, when you need the keys and values, you project this latent vector back up to get the states you need. Since it caches only this tiny vector per token and reuses it for both K and V generation, it achieves really high arithmetic intensity.
That sounds very efficient per token, but you hinted earlier maybe parallelization issues again. What's the trade-off with MLA?
The trade-off comes back to distributed inference. Because MLA has this single, unified latent head representation that all query heads need access to. Guess what?
It has to be duplicated, like MQA's single head.
Exactly. That single cache latent state vector has to be replicated across every single tensor parallel rank, every GPU. So even though the cache per token is small, the total memory used for the KV cache across all GPUs scales up linearly with the number of GPUs.
Ah, okay, so that duplication limits how large a batch or context you can handle across the whole system because you run out of total cache capacity faster.
Precisely. And it also makes systems using MLA a bit more vulnerable to workload imbalance. If you have requests with very different lengths in a batch, processing that single duplicated latent head can become a sequential bottleneck.
Okay, this setup perfectly leads into the new stuff, because this is where the paper we're looking at gets really interesting, introducing group-tied attention, GTA. It builds on GQA, Isa.
Right, GTA takes the GQA structure grouping query heads, shared KV within a group as its starting point. But the key academic innovation here is tying the key and value representations together into one shared state for each group.
Tying them instead of separate K and V projections per group, just one? How do they manage that without losing information? That seems like a core challenge.
It is, and it relies on some pretty insightful academic observations about how keys and values actually behave in transformers. Research pointed out a couple of things. First, Key representations often don't need their full dimensionality. They're effectively low rank, especially before you add positional information like rope.
Okay, so keys are maybe simpler than we thought, information-wise?
In a sense, yes. And second, studies found that you might not need to apply rope, the rotary position encoding, to the entire head dimension. Applying it to just a part of the dimension seems to be enough to maintain accuracy. Rotating the whole thing might be overkill.
Interesting. So if keys are low rank and only part needs rotating, maybe you don't need two full separate vectors for K and V.
That's exactly the thinking behind GTA. So for each group, they compute a single projection. Let's call it the tied KV state. The value part just uses this entire tied state.
Okay.
The key part is constructed more cleverly. Half of its dimensions come directly from the unrotated part of that tied KV state.
Right, the part that doesn't need rope.
Exactly. The other half, the part that does need the positional encoding, comes from a different, separate, single-head projection. This separate projection is rotated with rope, and crucially, it's broadcast or shared across all the heads within that group. Then you just stick those two halves together, the unrotated tied part and the rotated separate part, to form the final key vector for the group.
Wow, okay, so you cache the main bulk, the tied part, once, and you handle the specific positional stuff with a smaller, shared, rotated piece. That sounds quite memory efficient.
It really is. By tying the bulk of K and V and constructing the key this way, you essentially load one main combined state and reuse it. This cuts down memory transfer significantly. It roughly doubles the arithmetic intensity compared to GQA with the same number of groups.
Doubles it. Wow, and that means it halves the KV cache footprint per group compared to GQA.
Pretty much, yes, which gives you really substantial memory savings, especially in setups where you don't have tons of GPUs for tensor parallelism, exactly where GQA savings are less dramatic.
And critically, this academic trickery, does it hold up quality-wise?
Yes, that's crucial. The paper shows strong validation. Their experiments demonstrate that GTA matches or even slightly improves model quality compared to GQA across different benchmarks. Things like perplexity are similar or a bit better, and performance on downstream tasks holds up or sees small gains.
So efficiency without a quality hit, that's the goal.
Definitely.
Okay, now let's shift to the second innovation. GLA, grouped latent attention. This sounds like it takes inspiration from MLA, but tackles that parallelization problem we discussed.
That's exactly the motivation for GLA. It borrows the core idea from MLA of caching a compressed, latent representation instead of full K and V vectors. But it fundamentally redesigns the structure to make it play nicely with distributed parallel inference.
So how does it do that? What's the key difference from MLA's single latent head?
Instead of MLA's one large latent head, which the paper notes had a dimension of 4 times the hidden size per head, 4DEEF GLA uses multiple, much smaller latent heads. Each GLA latent head has a dimension of only 2 DEEFs.
Multiple smaller heads instead of one big one? And the academic breakthrough is that this structure allows for distribution.
Precisely. That's the critical insight for scaling these latent attention ideas. Because you have multiple independent latent heads, you can shard them across your tensor parallel GPUs.
Shard them, meaning each GPU only handles a subset.
Exactly. Each GPU in the parallel setup is only responsible for storing and processing the slice of latent heads that correspond to the query heads it manages.
Okay, I see the direct contrast with MLA now. MLA had that one big state duplicated everywhere. GLA breaks it into pieces and distributes the pieces.
You got it. MLA duplicates, GLA distributes. This massively reduces the KV cache memory needed per GPU as soon as you have 2 or more GPUs in your tensor parallel group. The more GPUs you shard across, the smaller the memory footprint per device becomes.
So what are the advantages here, both academically and maybe more practically?
Well, academically, GLA still achieves very high arithmetic intensity, similar to MLA, and roughly double that of GQA, around 2 times the number of query groups. So it's efficient computationally.
Okay.
Practically, the big win is that sharding design. It parallelizes super efficiently. Each GPU crunches on its local slice, reducing communication overhead and eliminating that costly duplication. And importantly, the paper shows it matches or even slightly exceeds MLA's quality on various models and benchmarks.
So again, no quality loss from this more parallel-friendly design.
Right. It shows you can get both efficiency and scalability.
And this better parallelization must have knock-on effects for real-world serving, right? Beyond just raw speed.
Oh, definitely. First, the smaller cache per GPU means you can fit larger total batch sizes or handle longer context lengths across your cluster. But maybe even more importantly, GLA is much more resilient to workload imbalance.
Imbalance, like when different users sends requests of very different lengths.
Exactly, which happens all the time in real services. Because GLA's work is sharded and distributed, one long sequence doesn't bottleneck the whole system the way MLA's single duplicated latent head could. This leads to much more consistent performance and higher overall throughput in realistic, messy scenarios.
That makes a lot of sense. The paper also really emphasizes that these cool algorithmic ideas, GPA and GLA, aren't the whole story. You need serious system-level optimization, too.
Absolutely essential. You can have the cleverest algorithm, but if the code running it on the GPU isn't highly tuned for that specific hardware, you won't see the full benefit. The authors clearly spent a lot of effort developing optimized kernels for GTA and GLA, specifically for hardware like the NVIDIA H100.
What kinds of tricks do they use in those low-level kernels?
They use pretty sophisticated techniques to basically hide memory latency and keep the compute units fed with data, things like software pipelining.
What's that?
It's where the kernel starts loading the data needed for the next computation step while the current step is still executing. Overlap of memory access with computation.
Okay, keeping things busy.
Right. And also warp specialization. They dedicate specific groups of threads on the GPU, warps purely to loading data from memory, while other warps focus just on putting the math. It's about dividing labor efficiently at a very low level.
So really pushing the hardware to its limits, trying to make sure even these memory-friendlier algorithms don't end up waiting on data.
That's the goal, yeah. Maximize utilization of both memory bandwidth and compute units. And the results are pretty compelling. The optimized GLA kernel, for instance, they show it being up to twice as fast as other highly optimized baseline, like Flash MLA in certain scenarios.
Twice as fast. In what cases?
Particularly in things like speculative decoding, where you might be generating, say, 2 potential tokens at a time based on a short query prefix. Even in standard single-token decoding steps, they measured around a 20% speedup. It shows high utilization of the H100's potential.
Impressive. They also mentioned something about optimizing paged KV. What was that about?
Right, so paged KV is a common technique now used in systems like VLLM. It manages the potentially huge KV cache memory more flexibly by dividing it into fixed-size blocks or pages, kind of like virtual memory in an OS.
Okay, helps avoid fragmentation, manage memory better.
Exactly. But there was a catch. For very small page sizes, like a page size of just 1 token's worth of K and V, which can be useful for advanced techniques like prefix caching, the overhead of calculating the memory address for every single token's KV data could actually become a bottleneck itself.
Ah, the address calculation got slow for tiny pages?
Yeah. So the paper introduces an optimization called distributed offset calculation, specifically for page KV. It significantly speeds up this address calculation, making even a page size of 1 really efficient. This basically unlocks the performance benefits of those small page sizes for use cases that need them.
Okay, bringing it all together, all this deep technical stuff, GTA, GLA, optimized kernels, how does it actually translate back to, me using an LLM? Less waiting, better service?
That's where the online serving benchmarks come in. They try to simulate a real service, multiple users sending requests at the same time, requests queuing up. And they measure the things you care about: end-to-end latency, how long from request to full response, and throughput, how many tokens per second the whole system can generate.
Right, the practical metrics. And what did GLA achieve there?
Significant gains. In one benchmark simulating a pretty realistic load, like 64 concurrent users, GLA slashed the median end-to-end latency by about 53% compared to MLA running with the same pure tensor parallel setup.
Wow, cutting the wait time in half, essentially.
Pretty much for the typical user in that scenario, that's a huge deal for anything interactive.
Absolutely. And what about the overall system capacity, the throughput?
Similar story. In that same benchmark, GLA boosted the token throughput by around 70% at that load. Across different tests, they consistently showed much higher throughput, sometimes up to 2x compared to the MLA baseline, especially highlighting the benefits of GLA's parallel design.
You stressed earlier that the parallelization approach of GLA was key.
Hugely important. The benchmarks really bear out how GLA's sharding strategy in pure tensor parallelism is just much more effective and frankly simpler than MLA's approach, which often relied on more complex hybrid setups, mixing TP and data parallelism to work around its duplication issue.
Right.
And crucially, as we discussed, GLA handles that real-world workload imbalance batches with mixed short and long sequences way better. The paper includes graphs showing GLA maintaining much higher throughput under those messy imbalance conditions compared to MLA's hybrid attempts.
Okay, the performance numbers are really strong. But the big question that always comes up with these kinds of efficiency optimizations: did they sacrifice model quality to get there?
The million-dollar question. And it's critical validation. The paper explicitly addresses this and confirms, no, these architectural changes and system optimizations don't degrade model quality. They tested both GTA and GLA across various model sizes, going up to a 1.47 billion parameter XL model.
And how did they measure quality? Standard tests.
Yeah, standard stuff. Language modeling perplexity, which measures how well the model predicts the next word, and a suite of common downstream task benchmarks, things like Winograndi for common sense reasoning, PsyQ for science questions, MMLU for broad multitask accuracy.
And the results.
Consistently good. GTA matched or even slightly improved on GQA's quality across the board. And similarly, GLA matched or slightly improved on MLA's performance on these same benchmarks.
Okay, that's reassuring. Quality preserved, sometimes even a tiny bit better.
Exactly. It demonstrates you can have both efficiency and quality. They aren't necessarily a trade-off if the architectural changes are well designed.
So, wrapping this up, what's the big picture here? It feels like this work on GTA and GLA is a really significant step forward in making these powerful models more practical, more usable.
I think that's absolutely the key takeaway. This deep dive shows that by really rethinking fundamental parts of the model, like the attention mechanism, and specifically designing them with the hardware realities of inference and decoding in mind.
Right, not just training, but how it runs.
Exactly. And then coupling those smart algorithmic changes, like tying K and V in GTA or sharding latents in GLA, with equally deep hardware-aware system optimizations, the custom kernels, the memory management tricks, you can unlock major gains.
Gains in what specifically?
Gains in per-token latency, so faster responses. Gains in overall system throughput, meaning services can handle more users or generate more text faster. And gains in parallel scalability, allowing models to run efficiently on distributed hardware and handle bigger problems.
Which ultimately translates to a better experience for anyone interacting with an LLM and makes deploying them more feasible.
Precisely. It really highlights the importance of co-design thinking about the algorithms and the systems they run on together, not in isolation.
This work definitely drives home that future AI progress isn't just about scaling up to bigger and bigger models, although that's happening too. It's also critically about making inference, the using of these models, drastically more efficient. Rethinking core components based on how chips actually work seems crucial.
Couldn't agree more.
So maybe a final thought for our listeners to chew on. This paper dove deep into attention. Given how models keep growing in size, complexity, and the demands we place on them, what other fundamental building blocks of today's AI models might be ripe for a similar kind of hardware-aware deep dive and redesign? Where else might we find bottlenecks that need this level of rethinking to keep pushing the boundaries?